So I chose to talk about heat engines and the Carnot cycle. These two topics are something that are usually discussed later in a thermodynamics course, but they're very important topics and they're used everywhere. So heat engines are used in power plants, they're used in your cars. Basically, any kind of thermodynamic cycle that involves doing work on your surroundings is really what a heat engine is. So they're really important, and they're based on the basics of thermodynamics. So the first law is obviously that the energy input is equal to the energy output. So energy is conserved. And then the second law is that the entropy of the universe is always increasing. So any kind of thermodynamic process is going to involve an increase in entropy to the universe. So I've drawn this little system right here. It's just a box with some gas in it, and there's a propeller inside the box that's connected to a mass outside of the box. So as this mass falls, it's going to cause the propeller to spin, and there will be work done on the gas, and we'll consider the gas to be the system. So this is the system, this is the gas, and that would imply that the work involved in this process is negative, since the surroundings are doing work on the gas, on the system. And then, so as this propeller starts turning, it's going to cause the gas to, it's going to transfer that energy into heat into the gas. And that gas will eventually lose this heat to the surroundings. So that would imply that the net change in heat of the system is also negative. So intuitively, according to the first law of thermodynamics, all it says really is that the energy in the system should be conserved. So in theory, it doesn't say anything about whether it should be reversible or not. But we know from intuition, if we tried to heat up this gas, if we took a blowtorch to this is my little blowtorch, it looks more like a duck, but if we put some energy back into this, it would not cause this propeller to spin, and it would not pull this back up. So that begs the question then, is there such a system where the work is positive and the net change in heat in the system is also positive? And that is what is known as a heat engine. So I've drawn a really simple heat engine here. It's just a piston with a weight on it that's holding down some gas. So, and then, so if we start out with some heat source, so this could be combustion, this could be burning wood, this could be a hot sidewalk, anything that's hot, and we apply this heat to our system. So again, the system is this gas. It's going to cause that gas to expand, and as that gas expands, it's going to do work on the surroundings. So it's going to push this let's redo that. It's going to push this up, this piston up, and lift up this weight. So that implies that the work is positive, since the system is doing work on the surroundings. Now, if we take this weight off, just remove it, then the heat in the system that was used to lift the weight is eventually going to leave and go to the surroundings. So that's our loss in heat, so QL. So since the system did work on the surroundings, we know that the original QH must have been greater than QL. So we'll say this, which implies that the work was positive. And then also implies that the net change in heat was positive. So that is what a heat engine is. It is a system that uses a heat source to do work on the surroundings, and in doing so does positive work and has a net change of heat that is also positive. So the next question then is, well, how efficient can we make this? what is the most efficient heat engine possible. And that is shown by what is called the Carnot cycle, which is what I've shown here. So same idea. It's a pretty simple system that's got it's just a piston compressing some gas in here, and we're going to apply some heat to it. So I've just drawn a little fire here. This is our heat source, and it's going to apply some heat to this. So as it applies heat, it's going to convert some of the, we have a liquid in here, and it's going to convert it into a gas. So that is an isothermal process. That phase change is isothermal. So it's going to keep expanding, and as that occurs, it's going to be doing work on the surroundings. So it's lifting, it's doing the work, and it's pulling these little, we'll call them DWs, for infinitesimally small amounts of work are being done at a time. And then once it reaches this stage, it's going to go through a transition that is called adiabatic. So in an adiabatic process, which is the transition from 2 to 3, there's no heat loss, but the temperature of the fluid inside of here will actually decrease. So the temperature of the fluid is going to be equal to the temperature of whatever our cold reservoir is. So that's over here. So that's called adiabatic expansion. So both of these are expansion scenarios. So until it finally reaches this point at 3 where it's fully expanded. Now, at this point, the fluid is going to go through a condenser, which is what I've drawn here. This little kind of like a condenser tower that you would see at a big power plant off the highway or something, and it's going to transfer its heat to the reservoir. So the heat is now leaving our system and into the reservoir, and but this is again an isothermal process. So the liquid is condensing. And then finally, we reach this point, and then these are being added back on. And we go through another adiabatic process where the change in heat is 0, and the temperature of our fluid increases back to the temperature of our original heat source of QH. And then at this point, the cycle will be repeated back to the beginning. So that would be the ideal process for a heat engine. Again, super useful. One of the most important parts of any kind of system that does work on its surroundings.